In this video lesson, we are going to learn about something called average atomic mass, sometimes referred to as weight average mass. This is part E of the Unit 0.2 notes, corresponding to the Rosengarten text, pages 6 through 11, I believe. Atomic mass. Let's take a look. On our periodic tables, we have what is called atomic mass. This is slightly different from mass number, as we learned yesterday in the last lesson. That mass number is equal to the number of protons, which for carbon is 6, and the number of neutrons that happen to be in an individual atom of carbon. Well, a carbon can have different numbers of neutrons, right? So each isotope of carbon will have a different mass number. Each individual atom will have its own mass number dependent on how many neutrons there are. But when we average all those isotopes' masses together, we're going to get an average. And averages are sometimes ugly because they're not nice whole numbers. So the quick answer to the question, atomic mass, is an average. It's a weighted average, and that's what we're going to be exploring, how this weighted average is determined today. So the term average atomic mass means that it is a weighted average and is calculated differently than a normal straight average. So a straight average, of course, if you were taking, let's say you had an 87, a 73, and a 92 as your quiz average, your test average, and your lab average in a science course, a straight average would just be 87 plus 73 plus 92. You would take that answer, and if we do that quickly on the calculator, you're going to get 87 plus 73 plus 92, right? That's 252. You would divide that by 3, and you get an average of 84. Okay, so that's a straight average. That means that the amount of importance in your overall grade that comes from quizzes, tests, and labs are all equal to each other. This is effectively 33% of your final average is determined from your quiz average, your test average, and your lab average. But sometimes teachers want different categories to convey a different significance to your overall value, and that's where we're going to be calculating what's called a weighted average. So let's say in a science course, your quiz average is an 87, but we only want it to not count for 33%, we want it to count for 15%. And we want your test average to count for 65% and your lab average to count for 20%. So first and foremost, what you need to do is take this percent, right? Percent is just 15 over 100, right? This is 15 over 100. This is 65 over 100, and this is 20 over 100. That's what percent means. So 15 divided by 100 is really just the number in your calculator as 0.15. 65% is 0.65, and 20% is 0.20. Well, what that becomes the factor that we are going to multiply by each of these numbers here. So 87 times 0.15. 87 times 0.15 in our calculators gives us 13.05. I'm going to put that number down without rounding. Next, I have 73 times 0.65. Without rounding, I'm writing that value down. And the last one, 92 times 0.20, and I've got 18.4, and I'm going to stick a 0 on there to maintain that place value. Once you get these three temporary values, add these up, good old plus sign right there. So 18.40 plus 47.45 plus 13.05 together adds up to a 78.90. So this student has an average of 78.90, about a 79%, less than the straight average of 84. And that is because the significant portion of their average is coming from their test grade, and their test grade wasn't quite as sharp as the quiz or the lab average. So that's the basic premise of how weighted averages work. We're going to now take a look and see how this works for isotopes and for elements. A note here. If I do not give you specific atomic masses for the individual isotopes, and only the mass numbers are given for the individual isotopes, then just use that mass number. If I give you a specific atomic mass for an individual isotope, you should use that information, and you'll see what that means here momentarily. Okay, we have 3 isotopes of iodine. Iodine 127, iodine 126, and iodine 128. Remember, this number here is considered the mass number, and if you remember, the mass number is the protons plus the neutrons in an individual isotope. If we were doing a straight average of the masses of these 3, we would add up these 3 numbers and divide by 3, and it would probably come out to exactly 127. Okay, but because in nature, 80% of all the iodine atoms that are found in nature, 80% of iodine has a mass of 127, 17% has a mass of 126, and only 3% of all iodine atoms have a mass of 128. So we want our average to reflect that abundance. So here's how this works. Remember these percentages? They're divided by 100, right? It's per 100. So when we do that, a decimal form of this becomes 0.80, 17% becomes 0.17, and 3% becomes 0.03. Now, no specific masses were given, so we are going to just use the mass number that was provided to us in the name. We are then going to multiply each one of these lines and get a temporary value, and we're not going to round these temporary values. Okay, so we're going to do 127 times 0.8, and we get 101.6. We get 126 times 0.17. Nope, wrong decimal place. 126 times 0.17. And we get 21.42. Let's go out to that second decimal place. 128 times 0.03, and we get 3.84. Add all of these up. We're going to add, and let's see, 3.84 plus 21.42 plus 101.6, and we get 126.86. Now, the mass unit that we use when we are expressing the average atomic mass is AMU, which stands for atomic mass units. Now, this is pretty close to 127. It's pretty close, but it is lower than the straight average of 127. And what that tells us is that it tells us that first of all, it tells you that the most common isotope is probably 127, because this is closest to 127. It tells you that because the average is slightly less than that, that there are some isotopes a little bit lighter than that 127. So that gives you some information. But here's what's really interesting. If we take a look at the periodic table, this number here, 126.86, if we compare that to iodine's atomic mass, which is 126.904, right? It is not the same, but it is very close. The reason why this number is different than the number we just calculated is because that these percentages are not very precise. These are rounded numbers. They also don't represent the specific isotope mass for individual atoms. These are still kind of rounded numbers. So the idea here's the takeaway. The number you get here should very closely match the periodic table. Okay, the atomic masses on the periodic table. Okay, let's take a look at another one where we have to get the information a little bit differently. And I think I am going to have to, this problem is a little bit goofy because it's spread out over 2 different pages. Apologize, here we go. All right, so here we have 4 isotopes of lead that are shown below, each with its percent by mass abundance and the composition of its nucleus. Using the following data, calculate the average atomic mass of the element lead. Okay. So each one of these isotope names are lead. There's 4 of them. 1, 2, 3, 4. But they're all lead, and they're all lead because they all have 82 protons. That's what makes them lead. But each one has a slightly different number of neutrons. And so the question is, what's the number that goes here? Is it the number of neutrons? No, it is not. It is the mass number. And the mass number, remember, is protons plus neutrons. So if we add up 82 and 122, right, we are going to see that that adds up to 204. And the next isotope, 82 plus 122, is going to add up to 206. The third isotope, 82 plus 125, is going to give us 207. And 82 and 126 is going to give us 208. Okay. All right. Isotope mass. No specific isotope mass is given, so we are just going to use the mass number here. Percent abundances. The first isotope, that's the 204 mass number, all right, is 1.37%. Then we have 26.26%. We have 20.82% and 51.55%. Okay, let's put those into decimal form, meaning you're going to take this number, percent, divide by 100, and you're going to get 0.0137, moving it over 2 places. The second percent abundance is going to work out to 0.2626. The third one is 0.2082, and the last one is 0.5155. Okay, so we're going to go ahead and multiply those 4 lines. And when we get 204 times 0.0137, this says go to the nearest tenth. We're going to go nearest hundredths place. So our temporary value here is 2.79. Our second line, 206 times 0.2626. We get 54.09, but the 5 is going to round that up, so we're going to call that 54.10. Our third line, 207 times 0.2082. We're going to get 43.10. Our last line, 208 times 0.5155, and we're going to get 107.22. Add those numbers up, and I am going to use the rounded number, so I'm clearing out my screen. 107.22 plus 43.1 plus 54.1 plus 2.79. When we add this up, we get 207.21. The final unit that we're going to use is atomic mass units. So AMU is the abbreviation there. And it's always a good idea to code check the periodic table, so we find, just to make sure we're in the right, certainly in the very close ballpark, we're going to look up lead, which is PB, is the symbol. PB, we have 207.2. So very close. Looks like that's a stray mark. I apologize. That is 207.21. In case you were confused where the decimal point actually existed in that number. So that works pretty well, right? 207.2 here on the periodic table as the atomic mass for lead. Feeling pretty good about how these numbers are arrived. Okay, so now we're going to look at problems where the specific atomic masses are given to you for the individual isotopes. So we will use those in our calculations. The element copper has naturally occurring isotopes with mass numbers of 63 and 65. Copper 63, copper 65. The percent abundance and atomic masses are 69.2% for the isotope with a mass of 62.93, right? So 62.93, that's the actual mass for copper 63. So 62.93. The percent abundance is 69.2%, which is 0.692. The other isotope is a mass of 64.93. So that's our copper 65. It actually comes in at 64.93 AMUs. And the percentage there is 30.8%. So in decimal form, that is 0.308. So we're going to multiply those two lines and see what we get for temporary values. 62.93 times 0.692. And we'll go to the nearest hundredth. So 43.55. Next line is 64.93 times 0.308. And to the nearest hundredths, that 8's going to round that 9 up. So we're going to go to 20.00. Is that the rounding there? So let's add those numbers up. We're going to add up the numbers as we have them rounded. 43.55 plus 20 is, of course, 63.55. Didn't really need to use the calculator there. But let's verify this on the periodic table. This is copper. The average atomic mass for all the isotopes of copper, copper is Cu, and if we take a look at copper on the periodic table, it comes in here at 63.546. Again, these numbers are pretty close to getting us that validation that we are seeking. All right, these next problems are we didn't set up a chart, but that's okay. A lot of times the chart's not set up. We just need to organize our data in a very similar fashion. Here we're going to calculate the atomic mass of bromine. Bromine is Br. One isotope of bromine has an atomic mass of 78.92. So let's call that bromine, it's effectively 79. It has a mass of 78.92 AMUs. And the percent abundance is 50.69, so 0.5069. We'll leave that math for a second. I'm going to line up the next line. The other major isotope of bromine has an atomic mass of 80.92, so we'll call that bromine 81. It has a mass of 80.92 AMUs. And the percent abundance of that one is 49.31. So as a decimal, that is 0.4931. So let's get our temporary answers of 78.92 times 0.5069. Rounding those temporary answers to the nearest hundredths place, we get 40.00. Our second line, 80.92 times 0.4931, is 39.90. Adding those up together, we get 79.90 AMU. And if we look at bromine on the periodic table to seek our validation to make sure our math is pretty good, we've got bromine right here with the atomic mass on the periodic table reading as a 79.904. All right, so that's looking pretty good. The last question is not actually a math question. There's 3 isotopes of silicon, Si. They have mass numbers of 28, 29, and 30. If we look at the average atomic mass of silicon on the periodic table, 28.0855, 28.0855, what does this say about the relative abundances of the 3 isotopes? Right? A straight average of these 3 numbers would put you at an average of 29. But it turns out that the weighted average is much closer to 28. What does that tell you about the relative abundances of the 3 isotopes? The idea here is that with the weighted average closest to 28, that silicon 28 is most likely the most abundant isotope of silicon on the planet. So that's what it means. So average atomic mass again, is a weighted average of all the isotopes of a given element. And the atomic mass is what is reported, this average atomic mass is what's reported on the periodic table. And it's different than the mass number, which is the individual atoms' number of protons plus neutrons. All right, there should be a problem set that corresponds with this lesson. Go ahead and try that. And otherwise, I will see you back in the classroom.